have to go to the.
Okay,
I might have to go to the
so
participants tab and assign it for me, because for some reason I don't see the polls button.
so I'll take care of it. Don't worry. Right?
Okay.
So, okay, folks. So this is the last of our series on convolutional neural networks, the fourth in the series. And so this is a continuation of lecture 3. We're going to quickly recap backpropagation through a CNN and wrap up what we did not complete in the last class. And then we're going to look at some modifications like transposition, scaling, and rotation and deformation and invariance, segmentation and localization of objects in an image, and time permitting, we'll discuss some success stories with CNNs, a little bit of history, basically. So here's the story so far. Shift invariant pattern classification tasks like, does this picture contain a cat? Or does this recording include the word hello? Are best performed by scanning for the target pattern, the cat or the word hello, using CNNs or their one-dimensional scan equivalent, time delay neural networks. Now, these are shared parameter models that can be trained using variations of backprop. So here's what we saw in the last class. When you want to compute, we use backpropagation to compute the derivatives of the divergence between the actual and desired outputs of the network with respect to network parameters. So when you want to perform backprop on a single training instance, in the first step, you're going to pass the training instance forward through the net till you get a classification output. Then you compute a divergence between the output of the network and what you want the output to be, the desired output. And then backpropagate the derivative of that divergence backwards through the net, all the way to the beginning. We use regular backpropagation through the final MLP layers of the net. Subsequent backpropagation from this final flat MLP requires modifications that consider the shared computation in the convolution layers and the pooling operations that happen in the pooling layers. So there are two distinct components that we have to consider separately when we're doing the backprop. For convolution layers, remember, a convolution layer consists of two operations. In the first, you compute a collection of affine maps. And the second, you apply activations to these affine maps to obtain output activation maps. So the affine maps at the Lth layer are represented using Z of L. The output activation maps are Y of L. And so our problem is going backwards, when you have the derivatives of the divergence with respect to Y of L, how do you compute them with respect to Z of L? And then, given the derivatives with respect to Z of L, how do you propagate the derivatives further back and compute derivatives with respect to the maps from the previous layer, Y of L minus 1, the L minus 1th layer, and also the derivatives with respect to the Lth layer filters. Now, this is for convolution layers. For pooling layers, given the derivatives with respect to the pooled output, we need to figure out how to compute the derivatives with respect to the input to the pooling. So with respect to the previous layer. Now, first we saw this. We considered convolution layers. In the first step, we looked at how we would compute the derivatives with respect to the affine maps Z, given the derivatives with respect to the activation maps. And this was very simple. So again, within each layer, you get a collection of affine maps which have been obtained by convolution over the previous layer. And then the activation maps are obtained by pointwise application of the activation function. So every component of every activation map in the Lth layer is obtained by applying the activation function to the corresponding component of the corresponding affine map in the Lth layer. So going backwards, if you have a derivative with respect to y, lmxy, which is the activation output, the derivative with respect to the affine value is simply obtained using the chain rule. the derivative with respect to z, lmxy, is the derivative of the divergence with respect to y times the derivative of the activation function itself. So we saw this in the last class. And so now we can assume that we have the derivatives with respect to every component of every one of these affine maps. I'll call them the affine. So these derivatives too can be arranged as maps because you have one derivative per component. So I'll call these the affine derivative maps for want of a terminology to describe them. So now, given the derivatives with respect to the affine maps, namely given the affine derivative maps, we now need to figure out how to compute the derivatives with respect to the activation maps of the previous layer, and also the derivatives with respect to the filters that computed the current affine maps from the previous layer activation maps. And we saw how to do this as well. We saw, for instance, that in order to compute any affine map, the contribution of the mth activation map from the previous layer was obtained by convolving that map with the mth plane of the filter corresponding to the activation map. So the contribution of this mth activation map from the previous layer to each one of these filters is obtained through the mth plane to each one of these affine maps is obtained through the mth plane of the filters. And so we visualized the operations and went through the math and found that given the derivatives with respect to all of these z's, namely given these the derivative maps for these affine values, the way we would compute the derivative for the mth map or the mth activation map for the previous layer was through convolution. What we would do was to take all of these mth layer planes of all the filters, which is shown by this, flip them left to right and top to bottom. So you're going to get one such plane. And because you have as many of these planes as you have output activation maps, output affine maps. So you're going to have one of these flipped planes per output affine map. We zero padded these affine maps, and then we convolve them with this collection of flipped planes, filter planes. And the result of that convolution gave us the derivative for y L minus 1m, namely the derivative for all of the components of the mth activation map of the previous layer. So this was step one. Step two, we also saw how to compute the derivatives with respect to the filter parameters themselves. And the way we did it, so again, the filters were of this kind. The nth filter generates the nth affine map, and the nth filter in turn is going to have several planes, one plane per input activation map from the previous layer. And so to compute the derivatives for all of these filter terms, all we did was to convolve the corresponding y map with the affine derivative map for the nth layer affine derivative map. So the nth affine derivative map in the nth layer. So to obtain all of the planes of the nth filter, we picked up the nth affine derivative map of the nth layer and convolved it with each of the activation maps in the L-1th layer. And that gave us the derivatives for all of the terms in the nth filter. We would do this for every one of the affine maps in the nth layer, and subsequently get the derivatives for every one of the filters. So we saw this as well in the last class. And so as a result, we have figured out how to do all of this. Given the derivatives of the divergence with respect to these maps, the activation maps in the nth layer, We figured out how to compute the derivatives with respect to the affine maps. We figured out how to compute the derivatives with respect to the filters, and also how to compute the derivatives with respect to the activation maps from the previous layer. Now, the procedure that we saw looked somewhat complex, right? So, but in fact, there's a cheap way of computing the derivatives without worrying about all the details we saw in the last class. I kind of briefly went over this in the last class, but let's actually look at this in a little more carefully. So here is how here is the pseudocode for the forward computation of CNN. You go through the layers. In each layer, you're scanning the input. So if I were to pictorially draw this, here's what is happening. For each layer, let's say you have an input. You're going to have several of these input maps. For each layer, you're scanning the input. So that's part of the convolution. And so this loop over X and loop over Y is scanning the input. Now at each position in the input, for at each position in the input, for each of the output affine maps, you're going to try to compute the corresponding position value in these maps. And the way you do this is you take a small filter-sized section of the input, and within the filter size section, you go over this entire section and compute an inner product, a component-wise product between the filter and the map behind it, and then sum them all up. So what is happening over here is, here it says you're going through all the filters. Within each filter, so observe, now remember over here that in the previous layer, you're going to have several of these maps, right? This is YL minus 1. So we're going to have several of these maps, and you'll be simultaneously scanning all of these guys. So if to compute the value here at this position, you're going to take a little window section of the same region of all of the Y maps. And then in all of these regions, you're going to perform a point-wise product, component-wise product of the filter value there and the underlying map. And then you're going to sum them all up. So that's what this operation does. This loop here, the DL minus 1 loop, this I loop is actually going over these maps. And then this one here, for X prime and Y prime, these X prime and Y prime loops, those are just sort of going over this little region within the filter. And then within the filters for these maps. And then at each X prime Y, so at each position, you're sort of scanning over that little window, and then you're computing a point-wise, a component-wise product of the filter value at that position and the underlying map value at that position. And this product is being added to the affine value. So basically what's happening here is that you're going over these little maps. At each point, you're taking a component-wise product of the filter and the underlying map, and then you're adding all of these up to compute this one z value, right? So that's what this pseudocode is doing. And once you've computed the z values for all the positions of all the z maps, you can just apply an activation on these guys and compute the corresponding component of the activation map. So is this pseudocode kind of making sense to you guys? Just give me a thumbs up or wave your hand so I can see if this is making sense. Yeah, that's all it is. So the X prime Y prime loop is just the loop within this little patch. Okay. So now this is important. It's important to understand that what is happening over here. Now, so this is going over all of the layers. Let's just consider one layer, right? Now, so here is something very interesting. If I want to just, I can do something very cheap. If I have this forward computation, right? What is the key component, key computation that's being performed over here? The key computation is z plus equals w times y, right? With the indices. So z lj xy equals w times plus equals, not the plus equals, w of lj I x prime y prime times y of L minus 1, I, x plus x prime minus 1, y plus y prime minus 1. The specific indices, we don't need to focus on it. If you look at it offline, you'll find out it all works out. But the key point is this, that as you're going through the computation, you are sort of scanning the input, and at each position, you're performing a component-wise product of two terms and adding all of these up, right? And the primary operation over here is of the kind z equals w y. This is from the previous layer. This is the filter. This is the affine value. And we already have d div over dz because we are backpropagating. So given this, I can easily enough say that d div over dw is going to have one component. The divergence is probably being affected by many things, but it's going to have one component, which is d div over dz times dz over dw, right? And dz over dw is simply y. So this is going to be d div over dz times y. And similarly, I can also write d div over dy, and I'm going to put a plus over here because you might have each w might be affecting many, each w might actually be affecting many different components in the maps. So they will accumulate. But the point is this: I can similarly write d div over dy is going to be d div over dz times w. So do you guys see how these equations come out? These two equations, how they come out of this one simple equation. Z equals wy tells me that dz or d div over dw is d div over dz times y, and d div over dy is d div over dz times w. So these two should be kind of obvious. So is this making sense to you guys?
Yes.
Right, so that's it. So all I'm going to do is, once I have performed the computation forward, I can just modify this code trivially by unwinding it. What am I going to do? I'm going to go backwards through my computation in exactly the same manner that I went forward through my computation, except that when I'm going backward through my computation, since I already have dz, I'm going to be using that to compute dy and dw. So this is going to be within one layer. This is the operation. Now, what I will do is, I'll explain this. In the forward pass, we sort of scanned like so, right? So in the backward pass, I'm going to reverse the scan and do this, go backwards. Then at each position in the forward pass, I performed a, z plus equals yw. I'm going to, from this, I'm going to go backwards and say, therefore, dy equals dz. Dy represents the derivative of the divergence with respect to y. dz represents the derivative of the divergence with respect to z. So I'm going to write dy plus equals dz times w, dw plus equals dz times y. That's all I'm doing. I'm just sort of winding my way backwards And each time I encountered an operation over here, since I already have the derivative with respect to the left-hand side, I can use that to increment with the derivatives for the right-hand side term. And so if you look at this equation, look at what's happening over here. This outer loop is winding, it's scanning the input backwards from the bottom to the top. That's what this outer loop is doing. And then within the outer loop, every single loop is working backwards, observe, right? And now, because the last operation over here was y equals activation times z, this is just simply redoing the code. That's it, right? You're not doing anything. You're just unwinding the computation. So take a look. You literally are just working with the code. So the last, when I work my way backwards, what was the last operation that was happening within this XY loop? I was computing y equals activation on z, right? So the first thing I will do is dz equals dy times the derivative of the activation. So from the derivative for y, I have computed the derivative for z. That was the last operation. So at this point, when I enter this loop, I have the derivative for z. At each point now, all I have to do is to increment the derivative for y by w times dz and increment the derivative for w by y times dz. I'm just unwinding the operations. I'm not even looking at the math. I'm not looking at the fancy operations. I'm just sort of unwinding the sequence of operations that I did in the forward pass. And I can do this simply by performing all my loops backward. Just reversing the same code. All that happens is that the loop indices are now going back in reverse order. That way I make sure that anytime I'm computing the derivative for some term, all the terms to the right-hand side have already been obtained. And then for every single line of this kind, z equals wx, wy, I'm going to get dy equals w times dz, and dw equals dz times y. That's it. This is the only change I need to make, and the whole thing kind of works. So if I sort of increment through if I also add in, this was just for a single layer. If I want to do this for all the layers, even in the case of the layers, you're going to, in the forward pass, you went from the first layer to the last. In the backward pass, you're going to unwind from the last layer to the first. But as far as the change in the code is concerned, it's quite trivial, right? So is this making sense to you guys? Questions? Right? And so this is simple, right? Very simple. And here's the beauty of it. And you can sort of recast this. This is a bug here. There should be a 1 colon out here. This is a mistake. And you can recast this in tensor form and vector operations in different ways, but this is really the basic idea. And here's the beauty of it, right? Suppose your forward pass had strides. So in your forward pass, if you had strides, what you would have done is not scanned directly like this. Instead, you would have done something of this kind. You would have computed here, 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 and here. So your forward pass would have jumped values, right? So when you perform a computation scan with strides, you don't have to worry about any of the zero padding and all the other fancy stuff we saw in the last class. When you unwind, you're going to go back in this order. That's it. So you basically undo your loop. You reverse your loop and ensure that you walk over the same points that you walk forward. So this is so all we did over here is, if I'm doing this if my forward had strides, all that happened over here was that in the backward pass, I walk back over the strides as well. So the forward code is retained as such. I just flip the order and flip the indices. So if I flip the order in which I go through the loops, I have to keep track of the indices to make sure that I'm indexing the appropriate values. But otherwise, the code is quite trivial. So again, you don't have to do anything fancy to remember it, right? So as you can see, if you just think of it from the perspective of code, this actually becomes much, much simpler, right? So I believe there's a hole over here. Why can't I? So you have a pole, guys. Ten seconds, guys. Let me stop this here. All of these are true, right? That's all we do. We're just going to run all of the loops backward. Convert every operation of the form y equals fz to compute dz equals dy times f prime of z. And every operation of the form y equals wz is to say dw plus equals dyz and dz plus equals dyw. Note the plus equals. That's because a single value might be used in the computation of multiple output terms. So when you walk back, the little key magic over here was that all the derivatives are initialized to 0. And anytime you do something of this kind, all you do is increment. So this loop is assuming that dy has been obtained, right? But observe that over here, dy is being obtained. You see this bottom over here? Given the dy of the lth layer, this is computing every single dy term of the L-1th layer. You're also computing every single term of the filter.
So in
that
the
coming
poll,
across?
in the poll, it was mentioned that we are calculating dz. So
the poll was incomplete. It didn't say everything that you. So let me show you the poll again, right? So you are computing. You're running the loops backward. You're computing the derivative for dz from dy, the dy of the next layer, right? Of the kind. And
so,
then the dy of the previous layer is being computed.
Yeah,
Make sense?
Yeah.
This should have been dy.
Exactly. Yeah.
There's a bug over here, but yeah, there's a mistake. I'll fix it. But you get the concept. It's very simple. So now so we have fully dealt with convolution layers. Let's consider the pooling layers. We saw this in the last class as well. For pooling layers, we saw pooling is a mechanism for aggregating values from a small window, either by taking their mean or their max or some other such permutation invariant or jitter invariant function. So, and typically we do this with a stride greater than 1. So if the resulting operation is if the aggregation operation is a max operation, it's going to be max pooling. And so here, and with 1 value per stride. So at each position, you're going to get 1 value from the window, and that's your pooling operation. And if you're performing max pooling, within each window, you're always going to output the largest value in the window. So for example, if this window is 1365, you're going to output the 6. Now the pooling itself is always performed in a 2-step process. So for this position, what you will actually do is say the maximum value over here occurred in the 0, 1 position. And so you're going to store the 0, 1. And then here you're going to read the value from the 0, 1 position and copy it over. So you keep track of where the maximum came from. Now, so when you're going backwards, I'm going to assume that this is the y, right? This is the output. So when you come backwards, you have already got the derivatives for this guy. And from here, you need the derivatives for the input. So you have the derivatives for the output of the pooling. You need the derivatives for the input. Now observe that we're only copying the maximum value over, right? So only the maximum value influences the output of the network. These three guys don't change. They don't affect the output at all because they are discarded by the max, which means that if I perturb this one from 1 to 1.01, it's going to make no difference at all to this output. In other words, the derivatives of all of these terms that were discarded is going to be 0, right? On the other hand, as far as the maximum guy is concerned, every small perturbation over here is going to reflect exactly over here. So the derivative that you computed at this point must be copied over to this location. So when we actually perform a when we do a back propagation through the max pooling, the derivative for the input map is the same as the derivative for the input map is the same as the derivative for the output at the max location, and it's going to be 0 otherwise. That's what this equation says. So you're going to assume all the bad numbers are distinct. If they're not distinct, if you have multiple of these, you could pick just one, or you could split the derivative uniformly across all the max guys. But assume they're all distinct. It's very unlikely that they will be identical in any case. Okay, so here is the pseudocode, right? Remember, max pooling is done map by map. From each activation map, you're going to perform a max pooling locally only over the map. So you're going to go individually over the maps. Within the maps, you're going to walk forward by stride. And at each position, you're going to look at a small window over here. And you're going to find the position of the largest element in the window, and you're going to copy it over. So that's what the max pooling does. So when you compute the derivative, all that happens, you're going to do the same thing in the code. You're going to go backwards, but it doesn't really matter. And you're going to say that the derivative at the maximum location is incremented by the derivative of the output. Now you'll observe that there's a plus equal to over here, and that the derivatives have been initialized to 0. This plus equal to is because when you're sliding forward, the same y position might have been the largest value in two or more adjacent windows. If the stride is lesser than the width of the window, then a single y value could potentially contribute to multiple output positions. So you have to add over all of the positions that it could have contributed to. That's why this is a plus equals. Which, pictorially speaking, what this means is that if I'm doing a max pooling here, and then I slide forward and my next window is like so, then if this guy is the maximum in both of these windows, in the output, that value is going to get repeated twice, once for the first window and the second time for the second window. And so when you compute the derivative for this term, you must add the contributions of both these guys in the output. This is YL minus 1, this is YL, right? So that's why you have the plus equal to over here. But as far as doing the back propagation to the max pooling layer is concerned, that's quite trivial. In mean pooling, we do the same kind of pooling operation, except instead of computing the maximum value, you're going to compute the mean of this window. And so here, for example, we have 1, 3, and 6, and 5. The average of these is 3.75. That value is going to be copied out here. Arithmetically, if this window is k cross k, then the mean is the sum of all of these values divided by k squared, because you have k squared terms over here. Now, when you compute the derivative, all of these guys are going to contribute equally to this derivative over here. So going backwards, we are going to split this derivative equally between all the terms that contributed to it. So if you have d div over dy over here, there are 4 elements here. So you're going to get 1/4 of d div over dy being added to the derivatives, all 4 derivatives, the derivatives at all 4 locations. Again, this one is the pre-pooled, this is the window from the pre-pooled layer. This is the pooled output, which is this guy. So the derivative here is going to be uniformly distributed over these 4 terms. In general, if the pooling window is k cross k, this derivative is going to be divided by k squared and distributed uniformly over all k squared terms. In pseudocode terms, where it's again, it's much easier to see this in terms of pseudocode. Here is the pooling, the mean pooling. Again, it's done individually over the maps. All pooling is done locally within a map. And so at each, you're sort of scanning through the input at some stride. At each position, you're reading a little block, a window of the input, computing the mean, and copying it to the output. So when you do the backprop, all that happens is that you're going to take the derivative. This should have been a dy, I'm sorry. You take the derivative of that output divided by the size of the window and add that much to every single position within the window. So pseudocode wise also, it's actually a very trivial operation. So again, you're going to initialize all of the terms, the derivatives to 0. And over here, the contributions are going to be plus equal to. This automatically accounts for the fact that some values could contribute to more than one output. And so we've shown how to compute the derivatives. Where should the dy be? Oh, sorry, that's this guy, yeah. This should have been 1 over k squared dy to the bottom right. That's a bug. Yeah. And so we've shown how to compute the derivatives for every type of layer in the CNN, including every intermediate output and every filter element. We can embed these in a gradient. Give me a second. So we can embed these in a gradient descent framework and train the network. And so the story so far, convolutional neural network is a convolutional neural network is a supervised version of a computational model of mammalian vision. We saw this last week. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, downsampling layers that operate over groups of outputs to reduce network size. The parameters of the network can be learned through regular backpropagation. Pooling layers must propagate derivatives only over the max pooling layers must propagate derivatives only over the maximum element in each pool. Other pooling operators have to use similar gradients or subgradients. Derivatives must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter network. So, questions so far? Any questions?
Professor?
Yeah.
Could you please explain again where exactly we're keeping track of the indices of the max element in max pooling?
So this is part of the forward code. Look here. I have PIDX is finding the maximum index of the maximum element, and then Y is simply reading, YMN is simply reading the L-1 layer map, the value of the L-1 layer map at PIDX. Do you see that here?
Yeah, I see. Thank you.
So again, when seen from the periscope of code, this whole thing becomes very, very simple to understand. Okay. Now, so in all of the explanations so far, we've assumed that as we go through the layers of a CNN, each layer either maintains the size of the previous layer or shrinks it. If the stride is 1, it kind of maintains the size except for boundary effects. If the stride is greater than 1, the output is smaller than the input. But can we do the opposite, where you start with small maps and the output maps are actually larger than the input maps? So to understand what this really means, it's easier to visualize it in 1D. So I'm going to assume a 1D scan. I'm going to use the bar representation that we introduced in the last couple of lectures. So each bar over here includes a number of neurons or filters. And when you scan the input, you're going to scan it with a bar. And you're going to get one output, 1 bar per scan position. So if the scanning is done with a stride of 1, you're going to get 1 bar for every input here. If it has a stride greater than 1, like over here where the stride is 2, you're going to get 1 bar for every 2 outputs. Or here the stride is 3, so you're going to get 1 bar over here for every 3 bars in the second layer, in the first layer. You get 1 second layer bar for every 3 bars in the second layer, because here the stride is 3, right? And here too, the stride is 3. So do you understand this figure? You must all be very familiar with this figure. This figure making sense to you guys?
Yeah.
Okay. Now, observe something over here. When I scan with a stride of 1, the size is maintained. If I scan with a stride greater than 1, the size, the number of bars is lesser than the number of bars below it. So the size decreases. But then, let's say I want to increase the number of bars over here, right? So if I have a stride of 3, I'm going to get only 3 outputs. If I have a stride of, say, 1, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 outputs at this layer. But now I want to have more than 9 outputs. I want to have many more than 9 outputs. In that case, so I want to have, say, 27 outputs in this region, right? How do I compute it? Because clearly, you want to increase the size. For example, if you've got a small image and you want to upsample the image and you want to get a higher resolution version of the image, that's upsampling, right? We do that all the time. So you could start off with thumbnails and create a portrait. So, but more importantly, this can potentially extract more features from the lower layers. So this upsampling layers have to be an integral version of your overall concept. Now, the problem is, if I want to compute things in this manner, I should be scanning according to this frequency, right? 27 times over this length. But what happens? When I scan 27 times, most of these guys are not going to get all the inputs they want. For example, look at this little pink box over here. Each of my boxes, if you'll see the previous slide, each of my boxes got 3 inputs. So let's say I decide my boxes need to have 5 inputs, right? So this pink box has got something to read over here. It's got something to read over here. It's got something to read over here, but at these 2 positions, it has nothing to read because those were not computed in this layer. Or this black box over here, none of the 4 of the 5 elements that it wants to read are missing, right? So in this case, if I were to ask you, how do I deal with this situation where I want to scan at a higher frequency, but when I do that, all the inputs I require at this layer are missing, or many of the inputs are missing. If I were to ask you what you would do in this situation, what would you do? Anyone?
Replicate the inputs.
Replicating is making assumptions, but that's actually not a bad idea, right? What you could do is just use vertical, which one do you replicate? You can't be sure. What I can do is introduce these virtual bars, all of which are 0 valued at the same frequency as this guy. And now I can scan. So basically, we are synthetically filling in these missing values with zeros. It doesn't even have to be zeros. These bars could be linear interpolations between the 2 adjacent bars. You could have other ways of filling in these things. But the simplest thing to do is to just fill in zeros. And now I can scan, right? So basically what we're doing is we are upsampling this layer by introducing zeros. And then the next layer is obtained by striding with 1 over these layers. Is this making sense?
Yeah.
Is this making sense, guys? Right? So why can't we just set which stride to be 1? If the stride is 1 up here, right? Let me go up. If the stride were 1, I can only compute a maximum of 9 outputs, right? If I want to compute more than 9 outputs, then that pink bar is going to be striding more than once for per bar over here, as you can see. And so in order to be able to compute all of these guys, you can do that. You can absolutely, making zeros filling in it with zeros is the simplest you can do. Linear interpolation is likely going to be cleaner. Okay, but you'll see why just filling in with zeros is also going to be a little more efficient. If I don't fill in with zeros, if I linearly interpolate, this is what you would do, and you're absolutely right. That's likely going to be a slightly better solution, right? Although you'll have issues when you're doing backprop. But then, if I introduce zeros, here's what happens. These zero guys, are they contributing anything to the output? They're not. You're multiplying zeros with weights and adding them, right? So the effective computation you're performing is just this. The rest of them never contributed anything to the output. And so, can we reset width equals 1 in the second layer? Can you explain yourself? I'm not sure what you mean by that.
Well, if I can I like, because this list size width is 3, right? So can we reset to 1 to make sure that 27?
Even if I have a width equals 1, having width equals 1 doesn't make a lot of sense here, but if I have width equals 1, these guys are all just going to be 0 valued, right? Because
Yes.
I'm filling in zeros below, so they're all going to be 0 valued. So if you want to upsample a width 1, really makes no sense.
Oh, okay.
Does it make sense to you?
How did you decide? Like, I know that right here you are saying.
Can you come closer to the mic?
Can you hear now?
Slightly better, yes.
Okay. So what I'm asking is, right now, I know that in the last layer, it's taking in five previous bars to compute it, right? But how about if you're only taking in, say, 3 previous bars?
So yes, that's a good question, right? I chose 5 just for illustration. If you took 3 or if you took 2, that's a design choice. The width of the layer is your design choice. And if that width is too narrow, then when you perform this computation, some of the pink bars are going to end up with 0 values. That's all. That's a design choice.
So do we need less virtual bars in that case?
No, because the number of virtual bars you're going to need is going to depend on how many bars you want in this layer, right? Regardless of the width of this kernel, how many bars you use in this layer is what decides how many virtual bars you have below, because you want a 1-to-1 correspondence if you have a stride of 1.
Okay, thank you.
Yeah, okay. So is it possible that during learning the filters that are learned are linear interpolation filters? So you could. You know, if you're a signal processing person, you know the best thing to be doing is to use something like a sink, right? So these are learned filters. Zero stuffing is probably going to be just fine. Now, the point is the actual computation with zero stuffing is this, correct? And so this is the explicit network for the upsampling layer, the layer that increases time resolution. Now, there's a fundamental difference between downsampling or size maintaining layers like these guys and the upsampling layers. In the downsampling, or what I call the regular layers, all of the columns are identical. Every column is reading 3 inputs from the previous layer, right? But if you look at the upsampling layer, you have different types of columns. all of these pink guys, all of the columns pointed to by red arrows are identically structured. Observe, right? This red arrow, this gets only one input effectively. Every bar pointed to by a red arrow has only one incoming arrow. Every bar pointed to by a green arrow has got two incoming edges, but it's shorter to the left and longer to the right. Those pointed by the blue arrow have two incoming edges, but it's longer to the left and shorter to the right. So basically, all of these bars to the top have different structure, right? So in terms of arrangement, what does it come out to be? When you're going up in the downsampling layer, in any layer, in any bar, the set of incoming edges, weights is identical. So if you look at these layers, these are downsampling or regular layers. This bar has the same set of weights as this bar, which has the same set of incoming weights, which has this bar, which has the same set of incoming weights. Whereas in an upsample layer, that is not the case. In an upsample layer, what you find is that in the previous layer, the set of outgoing edges, the outgoing weights is identical. So this pink sequence of pink bars is upsampled. So that means in the previous layer, the set of outgoing weights from each of these bars is identical going out. So does that make sense to you guys? Is this visualization making sense? If it's not, well, let's launch a poll.
There's another question in the chat. Still not sure why can't set stride to 1 in the first layer so that can have 27 bars in the next layer and won't need it to fill in zeros instead.
What if you want to have 36 bars in the next layer? Okay, guys, 10 seconds. Let's stop this one. Okay. The first statement is obviously true, right? Now, in the second one, in downsampling layers, the set of incoming weights in every column is identical, as you can see from the figure. In upsampling layers, so this should actually have been stated better, the set of outgoing weights in the previous layer are identical. So these options, I typed them in wrong, but in an upsampling layer, the set of outgoing weights in the previous layer are all identical, okay? So even with upsampled layers, the entire computation can still be viewed as scanning with a shared parameter network. So here, for example, this blue layer is an upsampling layer because the second layer has only 3 bars, but the third layer has, actually the third layer has only 3 bars. The fourth layer has 3, 6, 7. So that's an upsampling layer. But even with this upsampling layer, you can see that what you're really doing is scanning the entire input with this MLP. So the yellow triangle shows the actual network that's scanning the input. Even with an upsampling layer, you're just scanning it's just an MLP scanning the input. Now I'm sort of animating how the computations are performed in the upsampling layer. Actually, this is what going over, right? Now, so here's how the computation of an upsampling layer happens. Say this layer has been fully computed, right? The pink one here. Now, if you're upsampling, we know the locations of these bars, so we can initialize them all to 0. then the computation proceeds left to right. As we scan left to right, as we arrive at each bar and as we arrive at each bar in the lower layer, that lower layer is going to push its value up. So as you go left to right, first this bar here is going to push its value up into these three guys and increment whatever is there. Then this guy here is going to push its value up into these three bars and increment its whatever is there, and so on. So this, as a result, this whole thing, there's a sort of change in the manner in which values are computed when compared to regular downsampling layers. In a regular convolution where you maintain the size or you downsample, then we compute a bar, we compute this bar fully from all of its inputs before continuing to the next bar fully from all of its inputs, right? So this computation is roughly equivalent, is the computation of any one bar is the affine value at any one bar is roughly equivalent to multiplying the set of y values in the lower layer in this region in this layer by one row of the shared of the scanning network at this layer. So it's like multiplying these guys by one row of the weights matrix will give you the value here. In the upsampling layer, we push values up from the lower layer bars. So the lower layer activations are now invoked. So what happens as you go left to right, now each bar actually gets invoked multiple times, but now the lower layer bars are invoked only once. Whereas in a downsampling layer, the lower layer bars may be invoked multiple times, but the current layer bars are always invoked only once. So here, what is happening is that each lower layer bar multiplies one column of the weights matrix and pushes it up to the upper layer bar, which gets incremented. So alternately stating, you can say that each lower layer entry is multiplied by one row of the transposed weights matrix, because it's multiplying one column of the weights matrix. Compare these two. It's I comma colon, this is colon comma j. So this one multiplies one column of the weights matrix and pushes it up, or alternately it multiplies one row of the transposed weights matrix and then pushes it up. And so if you want to think about it in terms of the standard multiplication operation, the weights matrix that is used here is a transpose of the weights matrix in an upsampling layer is the transpose of the weights matrix that's used in a downsampling layer, because here you're pushing up. And so this kind of convolution is often called a transposed convolution. It's just terminology. All I'm doing is explaining why it is called so. There's no need to get bogged down with the details of that, right? So we've seen the 1D convolution version of upsampling layers. Let's see it in 2D. The 2D operation follows exactly the same principle. So let's say I want to start with this map and I want to produce a larger map. The first thing I will do is to upsample this map by introducing zeros. If I want to sample it by a factor b, say 2, I'm going to introduce b minus 1 zeros between any two rows and any two columns. So here b was 2, so I'm introducing one row of zeros between any two rows and any two columns. And now I'm going to convolve these upsampled maps with my filter to produce the output. Now, in practice, you won't actually explicitly upsample the maps. Just as we, in the case of the 1D case, as we did for the 1D case, the upsampling will be implicit. So let's say we want an output map that's b times the size of this input map. I'm going to create an empty map of zeros that is b times the size of the input field. And then I'll have some filter. And then I'm going to multiply this filter by the first element of this input and copy that value here. So the 0, 0 location is going to be copied to the 0, 0 location over here. And then I'm going to multiply the second value of the input by these filters. So here I have many maps. So this second value multiplies this plane, this one multiplies this plane, this one multiplies this plane, and then I sum them all up. And that value is now going to, because I want to expand by a factor of b, I'm going to stride forward by a factor b. In this example, b is 3. And so b is 2. So I'm going to stride forward by 2, and I'm going to copy the computed value over here. Then I'm going to multiply these this filter by these terms and sum up the planes. And now I'm going to stride forward by 2 again. I'm going to add, and I'm going to increment this portion of the output map with the value that I've computed. And I keep doing this as I go left to right. So what you'll observe in this process is that some locations, just shown by these light gray bars, only get one value. Others with this slightly darker gray are going to get 2 values. Those shown by these even darker boxes, they get 3 values. So different boxes in the output are going to get contributions from different numbers of elements of the input. So here is this making sense to you guys pictorially? Yes, no? No response. So any questions?
Why are we striding by B along the output instead of the filter?
So here, all I'm doing is this. Remember what we did when, yes, we are adding in the overlaps, right? Remember what we did when we were doing the 1D, right? So when we were doing the 1D, we just ignored all of the zeros because they don't actually contribute, right? Oh, come on. So the zeros don't actually contribute. So we ignored those, which is why when you look at what's happening, when you go left to right, I'm striding forward. Look at what's happening at the input, right? I'm computing from this pink value and filling in these 3 guys. Then as far as the output is concerned, I'm jumping forward by 2, right?
Right.
So that's exactly what's happening here. When I ignore the zeros and just do the explicit computation, I'm going to be jumping forward by the stride. That makes sense?
Yeah.
Yeah, okay. So here is the pseudocode for the expanding convolution. I'm sort of looping through exactly as before. And then the only thing that happens is that when I fill in the z values, I'm striding. The z values have been initialized to 0. I'm striding on the output, not on the input. I'm striding on the output. That's the only, that's the key component. And so as far as backpropagation is concerned, backpropagation for upsampling convolutions is exactly like backpropagation for regular convolutions. So what happens is that when you compute the derivative going back from the z to the y, you're going to end up computing derivatives for the upsampled maps of the previous layer. And so remember, when you were going forward, you took this guy, you upsampled it by filling in zeros, and then you scanned with a stride of 1. That's what you effectively did, right? So when you go back, you're going to get derivatives for these upsampled maps, and you're going to have to drop all the unnecessary ones and retain only the entries corresponding to the actual input maps. You can also use the trick that we just saw in earlier, where you can just start with this code and just work your way back, unwinding, and you don't have to worry about the niceties of strides and such like. This will just work out. I'll let you figure out how this code must be modified for backprop when you have an upsampling layer. So I have another poll, which is this one. 15 seconds, guys. Let's stop it here. This one was slightly harder than the previous ones. Both of these are true, right? I explained the first point pretty carefully. But if you use the same logic for the filters, the second one will also be true. I think I set up the poll wrong, so you only got to choose one or the other, but both these statements are true. So, well, at least it gets the point across. Okay, some final topics. CNNs are shift invariant models. They can detect a pattern regardless of where it occurs in the input. So it will recognize both of these pictures as having a flower. But if the CNN is trained to recognize pictures of this kind, will the same CNN recognize the figure to the bottom left as having a flower? Anyone? Will the CNN that recognizes flowers in the first two images recognize that the one to the bottom left has a flower? It will not, right? What about the one in the middle? Also no. And what about this guy? Also no, right? Because this is rotated. This is a completely different scale. This is inverted, right? These are transformations on the same basic pattern, yet a CNN that has been trained on the upper guys is not going to recognize these guys. To make it recognize the ones at the bottom too, you're going to have to add many copies of these lower images in your training set and increase the size of your CNN, and the whole thing can get very expensive. So the basic CNN formalism doesn't account for such transformations. We need to make the model, we need to explicitly make the model transform invariant. And to see how to do this, let's take a different perspective of shift invariance. What the CNN really does is to, if you're looking for a pattern, it makes many copies of the pattern it's looking for, and one at each position of the input, and it looks for it there. So basically, it's shifting your basic pattern, making copies by shifting it and looking for all of them simultaneously. It's just that we're implementing this copying and search in the form of a scan. Now, so we can generalize this, and instead of just looking for shifted variants of the versions of the pattern, we can also look for example, the instance rotated by 45 degrees and then shifted. So for this, we'd make two copies of the filter, one regular, then we would rotate the filter by 45 degrees, and then we'd scan the input using both the original filter and the rotated filter. And now this is going to be able to recognize the pattern if it occurs in its native form, and also if it is rotated. We can generalize this. Instead of looking for just shifted versions of the pattern, we can look generally for transformed versions of the pattern, including various kinds of transforms. What we'd have to do is to list all the transforms we want invariance to. So this is fine-grained. If you want rotation invariance, each angle of rotation is potentially a different transform. For scale invariance, every scaling factor is a different transform. So for each filter, each of these filters, you're going to make one copy of the filter for each transform in your list. And then you're going to scan the inputs with every one of these scanned filters, and you will get several maps from each filter, one for each transformation of the filter. And the next layer of the network will have to consider all of these jointly. And if you do so, then the network is going to become invariant to all of the transforms that you have considered here. So at the pseudocode level, here is the usual scanning. You scan the input, go through the filters, and each filter chunks out a section of the input, computes the affine term, and then applies the activation. If you want transform invariance, you add an extra loop. Each filter is first, we transform each filter according to every one of the transforms that we want to consider. And then we're going to compute the inner product between the segment and the transform filter, and then the activation. So you're going to get as many activation maps as you have transforms. This really should have a T. This code is buggy. There's going to be an M, T. And again, for back propagation, you can use the same trick we had before. We can just invert the code here and perform the back propagation. So one thing to observe is that when you compute derivatives, we need to keep in mind that each one of these transformed versions of the filter are derived from the same underlying filter. So when we back propagate derivatives, we will initially get derivatives for these transformed filters. So we must back propagate the derivatives through the transform to update the basic filter. So you want to update not the transform filter, but the basic filter, which means, of course, that you need some kind of a point-to-point correspondence between the original filter and its transformed version, so that you know where to copy the derivatives into. I'll skip the details of this. I'll leave this as an exercise, but this is only meant to give you a general idea. And so here's the story so far. The things that we've added is the parameters of the CNN can be learned through regular backprop. Like a regular MLP, individual layers may either decrease or increase the span of the representation learned. And the model can be easily modified to include invariance to not just shift, but also to other transforms, although these tend to be computationally painful. Now, the idea of the CNN is to recognize that the input includes the desired class regardless of the position. That is, that this image has flowers in it regardless of where the flower is. But can we also locate the object? Can we find the precise location of the flower? Now, this information is in the CNN, right? So we should be able to extract it. And it turns out you can. The standard architecture is generally some variant of this setup here. We'll cover this in a recitation, but the basic idea is this. After the final convolution layer, we will have now two concurrent output layers. One of them predicts the class of the object. The other is going to predict the corners of its bounding box. Then you're going to rotate the filter, because you want all of the maps to have a correspondence. If you rotate the image, then all of the maps will have different shapes and sizes. For example, if you're scaling, right, then the maps are going to be the fact is a flower and a rotated flower are the same pattern. This commonality is going to be ignored if you have separate networks, right? I mean, it doesn't matter whether this little fruit I'm showing is this size or this size, it's the same fruit. If you have a different network for each position, you can see how that's going to blow up, right? Make sense? Igli? I guess. So why are you unconvinced?
So if we produce more maps by transforming the filters, I feel like we will have a lot more parameters involved.
No, you don't, right? No, you don't. You're transforming the filter, but these derivatives are all being shared. They're being contributing back. So you're going to be updating just the original filter.
But how about the last layer? Wouldn't it be connected to more transformed maps now?
So over here, yes, but you're increasing the depth. You're basically you're increasing the size of the stack over here. So in that sense, you will have more parameters. But nevertheless, this has the advantage that at this layer, you're sharing the updates. And so you're actually exploiting the commonality of scaled and shrunk flowers. Whereas if you had separate networks, that information is lost.
Okay, thank you, Professor.
And so Gladys, the bounding box is the square. Right. So it generally won't. So when it comes to resolution, there are different classes of images. We like to throw all of these things into one training set, but you really have to think of these as different classes of images. So anyway, yes, during inference, you're training the model and you're going to use the same, you're going to do the same operation during inference time, right? So that is the point of those transformations. It makes the inference transform invariant. So now bounding boxes. From the final layer, I can have two outputs. One of them will produce the class. The other is going to give you the corners of the bounding box. And then when you train the net, you'll have two losses, one for the class, which would be maybe a KL divergence, and the other for these corners of the bounding box, where you can have different kinds of losses, intersection over union or L2 loss, and that quantifies the accuracy of the bounding box. And the derivatives from both of these losses are going to be backpropagated to update the network. More typically, solutions have a two-stage process where they first segment the input into regions and then run this process on the individual regions. And hopefully you'll actually get to see this in a recitation. You can see this, use the same mechanism for pose estimation. Now the second output layer will predict the joins on a stick model of the subject. And if you ever walked, back in the day when campus was open, if you walk from the Hillman building to Gates, you walk down or from Gates to Newell Simon, you walk down the corridor, you saw Yasser Sheikh's demo, which drew your skeleton and it's scary good. That basically uses this framework where, in addition to detecting where you are, it actually has a second output layer which finds the locations of each one of these joints. And then it can draw a skeleton. Now, there are other model variations. I'm going to run about 2 minutes over, guys. Wait with me, bear with me. They have very deep networks with tens or hundreds of layers. These are generally composed into ResNets. You're going to encounter this in your homework. One particularly useful variant is depth-wise convolution. This is a common approach to reduce the number of filter parameters. Instead of multiple independent filters with independent parameters, we use a common set of layer-wise weights and combine the layers differently for each filter. So to understand depth-wise convolution, let's look at conventional convolutions again. We have a stack of maps in the input. You have a filter. That filter is going to have one plane for every one of these maps. Now, when you perform the convolution, each plane of the filter is convolving the corresponding input map. So the first plane convolves the first map, the second plane convolves the second map. And so you're going to get a collection of convolved planes, one from the combination from each of these planes convolved with each of these maps convolved with the corresponding plane of the filter. And then you sum all of these guys up to get your final output. So when you have a number of filters, each filter separately produces a stack of convolved maps, which are then added together to produce that filter's output map. So if you have M input maps, each filter performs M convolutions. This guy, each plane is going to convolve with the corresponding input map for each filter. In depth-wise convolutions, instead of having a separate stack of planes for every maps computed by every filter, which is subsequently collapsed, we produce one common stack of convolved maps for the convolved maps from the filter. But then, instead of simply summing all of these guys up, we will perform a weighted sum, and the different filters only vary in the weight with which these things are combined. So this means that you have one actual convolution filter which produces all of these maps, and then you're going to have different sets of weights with which these things are collapsed to compute these maps. So the big advantage of this kind of computation is the number of parameters in the network. If you have m input maps, and if you have n output maps, so that is the number of filters, and if each filter's face is k cross k, then each filter is going to have m times k squared parameters. And because there are n filters, the total number of parameters is n times n times k squared. Whereas in depth-wise convolution, you're performing this convolution only once. So you're going to have m times k squared filter parameters, which compute all of these planes. And then this is still going to give you m planes. But then each of them is going to be, these planes are going to be combined with different weightings to produce each of the n outputs. So this stage of the computation has n times n parameters, and the convolution stage only has mk squared parameters. The difference between nmk squared and nk squared can be very large. Also, because now the convolutions are only performed once, this depth-wise convolution is going to be n times faster than a regular convolution. So depth-wise convolutions are actually quite popular when you want to make your model smaller and faster. And so the story, extending our story so far, our models can be easily modified to include invariance to other transforms. We can also make predictions related to the position and arrangement of the target object through what was effectively multitask learning. And several variations of the basic model exist to obtain greater parameter efficiency, better ability to compute derivatives, etc. And so one final topic, what do the filters learn? What are the receptive fields? Now remember, each filter is really just a neuron scanning the previous layers. So the kind of patterns the neuron responds to is called its receptive field. You expect these patterns to get more and more complex as you get deeper into the net. The receptive field for the first layer neurons is simply just the pattern of the weights. They look for inputs that look just like the arrangement of their weights. For higher layer neurons, the actual receptive field is not immediately obvious and must be calculated. And we can do so by setting the output of the neuron, for instance, to 1, and then using backpropagation. You set the output to 1, use backpropagation and see what pattern that comes up with. And that actual pattern is going to depend on how you initialize what input you begin with. So here are some typical examples for an image classifier. I think this is from Krzyzewski's paper. The lowest layer neurons have these receptive fields, which I've shown at the bottom, which look a lot like Hubel and Wiesel's discovery about cat's eyes. Now, for different output classes, so if I have different output classes out here, and then backpropagate the class label and find the receptive fields for the different neurons, here's what you find. For faces, the lowest level neurons get parts of faces as their receptive fields. The higher level neurons get face-like patterns. If you set the output, the network to be network's output to be a car, lower level neurons capture car-like parts of cars. Higher level neurons capture car-like patterns. Similarly, for elephants, these neurons get elephant parts. The higher level neurons get elephant-like structures. For chairs, these get chair-like parts. Chair parts, these get chair-like structures. So again, as you can see, as you get deeper in the net, the patterns that the neurons respond to are more complex and, in some sense, full. So there are some more slides. I'll leave you to actually read the slides. There isn't a lot of material there that you couldn't just get by simply reading the slides. I'll stop the lecture right here. We're at 8:14. I'll stop the recording. And if you have any questions, I can take them.